Welcome. This is the first video in the series on Principles of Radiographic Exposure 2. In this series, we will discuss computers, computer radiography and direct radiography, image processing, post-processing, PACS, and other hospital and imaging systems. In this video, we will have an introduction to computers, talk about analog and digital, and go over some basic electronic components. We'll start with the history. So we'll start with a history of computers. In 1842, Babbage designed an analytic engine. This was the first design of a mechanical device that could solve equations. It was built more recently because at the time they didn't have the manufacturing processes to actually do it, but it is actually functional just based on his design all the way back in 1842, so that's very interesting. In 1936, Alan Turing wrote a paper on computable numbers. Modern computers are based on this. Later developed the Turing-Welshman bomb, which it was used to decipher the Nazi codes in World War II with the Enigma code. Okay. In 1939, John Antonoff and Clifford Berry designed and built the first electronic digital computer. So 1939 was the first digital computer, where the Turing machine was mechanical, okay, and electronic, all right, but not necessarily digital, okay. And later we'll talk about the difference between digital and analog. In 1943, British built the Colossus during World War II and remained classified until 1976. So they didn't even declassify this 1943 device that they made until 1976, because all these things were right around World War II. Clearly with the 1936 and you see the 1944, even with the ASCC, first general purpose computer. A lot of energy was being put in to computers. A lot of energy was being put in and resources were being put into a lot of different things during this time that weren't looked at before because of the war, okay, because of World War II. So governments were, giving out money to research things and all this kind of stuff that wouldn't necessarily have been done at that time. So that's why these dates are close, where a lot of development starts happening right before and then right after World War II. Okay, with 1946, first general purpose electronic computer, the ENAC, was made. In 1948, William Shockley at the Bell Labs developed the transistor, and here's a picture of him on the left. The Bell Laboratories developed many different useful products in electronics and circuitry throughout the 40s and the 50s. Okay. UNIVAC 1951 was the first commercially successful general purpose computer, and it stored electronic programs. So this was the first actual computer that was general purpose and could store programs. So general purpose means that it isn't just designed for one task, for just solving one type of problem or anything. So and it could be programmed in different ways. Okay. In 1951, there has been 5 different generations of improvement. Okay, since 1951, there has been 5 generations of improvement in computers. All right, so the 1951 vacuum tubes were being used, which is a fragile glass device. Computers were very heavy and large. Low-level programming was available. No operating system were on these devices. So in 1958, transistors saw commercial use, a device that amplifies or opens a or closes a circuit. Okay, so a transistor is just a device that works like a switch. Okay, we'll talk more about that later. But uh, it and there were reduced dimensions and price. Okay, this was the first time there was like CPUs, which is like central processing units, and memory. Okay, and that was due to transistors. A vacuum tube was also could be like a switch. Okay, could be like a three-way switch, two-way switch, and they developed different types at this time, but they were large and heavy. Okay, and then the transistor could get smaller and smaller and smaller um, over time from the first one that we saw on the last page, and now you can put a bunch more together. Okay, and you can use those in different ways to create a central processing unit and to store memory in that fashion. So in 1965, integrated circuits, which is a variety of transistors on silicon chips. Semiconductors, this is the first time that what would be considered a semiconductor would be created and utilized. This creates higher speed and reliability. Okay, so now we can have higher level programming. Low level programming that we talked about before is where you're actually programming on the chip level. Okay, so you're actually doing the binary or assembly language, which is just above binary. And higher level programming is where you can actually type words that relate to um, that can relay to the compiler, to the computer, um, what processes to do. Okay, and then it handles all those basic processes. Where if you're in assembly, you're actually changing things called registers and pointers and things like that. Okay, um, individually. So in 1971, microprocessors were developed. Okay, this is known as large scale or very large scale integration. Okay, where 1965 was integrated circuits, now we're large scale, very large scale. One chip can contain all the circuits required to perform arithmetic, logic, and control functions. Computers became more user friendly, and you could have private computers, like personal computers started to become um, possible at this time. Okay, they're still very expensive, and nobody had them. Typewriters and things like that were still the big thing in offices. I mean, in the 1971, right? But big businesses and things, they could afford to have them. And even some individuals. So large scale, very large scale integrations where there's millions of transistors on a single chip, okay, a single silicon chip. Um, and then nowadays, there's billions of transistors on a single chip, okay. Um, Present artificial intelligence, okay, this allows computers to use algorithms to develop new algorithms to solve a problem. So the computer is, so the artificial intelligence is where the computer is coming up is is working in a way where it's coming up with its own solutions to a problem without necessarily being directly, where it's not necessarily directly programmed to solve that problem. Okay, um, it's the highest speeds and smallest size computers right now. There's like system on a chip where, especially in phones and things like that, and the small computers that are out now, that the whole system, the GUI or the GPU, the CPU, and all this can be on a single board, on a single chip. Okay, um, the boards might be referred to as PSC. Okay, boards. Okay, I mean PCB boards. Okay, printed circuit boards. Okay, so but the whole computer can be on a single chip, okay, and these can be increasingly small at this point, okay. Quantum computing is the next thing that's being developed, and at this time it seems promising, but there's a lot of difficulties to overcome, okay. So if those difficulties, and are overcome, then their quantum computing can change the face of computers for years to come. Okay, um, so at some point in the past, it wasn't thought that a computer could fit in a room, right? Um, and then later on, it wasn't thought that a computer could be affordable for a person, and so on and so forth. And you could never walk around with a computer, right? Even at one point. And now your phone, is a very uh, strong computer. It's practically a supercomputer from 15, 20, maybe maybe 25, but 15 or 20 years ago, it's practically a what a supercomputer might be capable of. Um, so quantum computing could very well be a reality um, at some point. We talked about the four generations here. Okay, now we got just a couple pictures to go with it. So an integrated circuit is something that looks like this. Okay, it could have several. Um, this is like a 555, which I think like a type of timer circuit, but the IC. But the it could have several uh, transistors and resistors and other kind of things in there to make it operate the way it needs to. But but it could also have hundreds of thousands, in this. Okay, a CPU would be no smaller, no larger than a what's inside the NIC, and that could have billions. Okay, um, so we talked about the electronic tube. So this is what the tubes look like. Okay, big, heavy. Uh, Objects, and each one of these could act like a transistor, or maybe a couple transistors, depending on how they're set up. Okay, with the inside and everything, how they were built. Um, but nowadays, a transistor is something on the order of like 30, 20, maybe 26. I think might be the newer generations. At this point, but like 26 nanometers, okay, would be like the gap um, between the gate, okay, of a transistor. So obviously, um, you know, tube style equipment um, couldn't produce what we have today. Okay, and so that's when we came into the transistors, then came into the IC, and then large scale integration, very large scale integration. Okay, so this is an individual transistor, okay, and what it looks like. And they usually have 3 pins, one for the source, one for the drain, and one for the gate. Okay. Um, so we'll go over some computer basics. All right. Um, Now that we've had the history of the computer, okay, we'll go ahead and we'll talk about, what is a computer, and what is it for. So a computer is an electronic device for storing and processing data. Okay, so you may not have thought about that before, but it's just an electronic device for storing and processing data. And typically, it works in binary form according to instructions given to it in a variable program. Okay, so there's a program, there's your operating system, okay, which can change different ways. If you update it or you change something about it, it's not gonna operate the same, right? On your phone, if you tap a space, an area on it, okay, so that's like your input on an area, and then it performs what you ask, it opens up the app or it does something like that. Then you tap in that same space, it's not going to behave the same way. Okay, so the program, so what's going on with the phone varies. Okay, um, depending on its last state, and what state it's in now. Okay, even though you're giving it the same input, right? So that's what defines a computer. Computer language gives computer instructions on how to operate. Okay. Um, the high level language, as we talked about, uses short English phrases. Okay. Um, but everything to the computer still goes back to binary. Okay. And we'll talk about like different systems of counting here, okay? So like a base 10 is what we know. Base 10 is what we count in. We go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. When we reach the 9, we add another place to the number, right? We go to 10, so now there's two places to the number, right? So that's base 10, all right? We start at 0, we're back at 0 after the 9, and now we add another digit, okay? So then it'll be 10. When we get to the next 99, then it's 100, right? Um, so now we have three digits. So in hexadecimal, uh, which is how computers think also, okay? It goes 0 to 9, and then it's A, B, C, D, E, F, okay? And then after F, it would go to what we would say 10, 1, 0, okay? And then it would go, then it would go 1, 1, 1, 2, 1, 3, 1, 4, right? All the way up to 1, 1A, all the way up to 1F, okay? Then we'll go to 2, all right? And after it gets done with all that, eventually we go to FF, okay? FF would be the last, and then it would go to 100, all right? And that's how that works. So in binary, it works just the same way, but it only uses bi, which means 2, 0, 1. So anything's a 0 or 1. It relates to on and off. Okay, it's either on or off, and that's the way that the transistor would work. Okay, in the computer. All right, the transistor can either be on or off. At its basic, there's some knick-knack things where it might be in different states, but for our purposes, the a transistor works just like a switch. It can either be on and off, and all these zeros inside the processor and inside the device leads to an output where the computer operates in a way that we want. Okay, the computer architecture. Okay, so we're talking about how it's built just a little bit. Okay, there's hardware and software. So hardware is like things like storage, memory, input-output devices. What might be some input-output devices that we could think of? Just think about that, input-output. So you're thinking about the computer itself, okay, and everything inside. What's like an input device for it might be something like a mouse. It could be something like a keyboard. It could be something like a microphone. All right. It could be a camera. All right. To us, in radiology, okay, an input device could be a CT scanner. Okay. So in the CT system, right, in the CT room, to the computer, to the part that's doing all the processing of the image and displaying the image and all this stuff and sending it off and all this stuff, the data that's coming in from the actual scanner, okay, that's being collected from the patient and processed there in a certain way to go to the actual computer, okay, that's just an input device to it, just like a keyboard, okay, much more complicated, right? But it knows how to handle the data that's coming in. It's coming in a certain way where it can handle it, and it knows what to do with it, and it displays the image. Okay, so something like the IR, okay, like the image detector in radiology. All right, to the actual computer, all right, that's behind the console and everything. The IR is just an input device. Okay, something that's an output device that's very easy is something like the display. Okay, so it's doing all this, it's processing it, and it's putting out the final product, which is the image on the display. Okay, on the screen. All right. So software is a computer program that tells the hardware what to do. Okay, and that's all that software is. Okay, it's just a computer program that is telling the hardware of the computer what to do. There's the operating system, okay, which handles all the tasks of the software with the hardware, okay. And the operating system could be like Windows, Linux, okay, Ubuntu. It could be different kinds of. It could be Android or the Apple OS, okay. It could be any of these kind of things on a computer or a phone. So the components, okay, of a computer, there's CMOS, okay, is a term that we'll be using through this class, okay. The is complementary metal oxide semiconductor. Okay, and you see a picture of CMOS right over here. Okay, so each one of these is a transistor. Okay, there's we don't need to get this far into it, but just for this explanation, there's two different types of transistors. Okay, there's an N type and a P type. Okay, so one when it's on, it will flow this way. One when it's on, it will flow this way. Okay, but these two together are complementary. Okay, N and P types transistors, and they can create an output here, okay? Depending on how the N's and P's transistors are put together, all right? Um, Another component of a computer is like a CPU, a central processing unit, okay? That handles all the arithmetic, we would say, of the computer. So at its core, these and logic of the computer, okay? So at its core, all these transistors together, they just do basic mathematical steps to the binary, okay? They can add, subtract, divide, integrate, derive, and depending on what the architecture of the chip is, okay, of the CPU, um, it handles these tasks in different ways, okay? There's also a GPU, which is a graphics processing unit, okay? These usually sit on top of each other in some way, or this can be a separate entity on the motherboard, okay? There's memory. There's two different types of memory. There's RAM, which is random access memory. This is fast type memory, okay? That changes quickly, so it loads things from the CPU to display out, okay, or it takes things in, sends it off, okay. And then there's ROM, which is read-only memory, okay. So random access memory goes away when it's powered down. It won't store any of the information anymore, okay. ROM doesn't need a power source, okay. So things like the BIOS or firmware could be considered ROM. So something like the BIOS, it's what initially tells the computer a computer system what to do when it first gets power, okay? And that's in read only. It doesn't need power to keep the information on it, okay? So input output devices, we talked about some of those. Touch screen could be another one in a radiology or your phone or a computer, tablet, right? And the motherboard connects all the components together. All right, so there's the motherboard, the memory can go in it, CPU goes in it, GPU goes in it, output devices go in through the peripheral channels, okay, of the motherboard. Computers and imaging. So we talked about some history, okay, and then we talked about some components of computers and what a computer is and all this. Now let's bring it together and talk about computers and imaging. Development of digital radiography in the 1979 analog to digital converter with a fluoroscopy tube. So the development of digital radiology began in 1979 with the analog to digital converter with a fluoroscopy tube. Computer radiography, CR, first appeared in the early 1980s. Okay, and we'll discuss more details in the next couple lessons when we get to CR. Early systems require almost doubling of technique. So the way that early CRs were built, you had to use more radiation, okay, than with film. That's what it's talking about. Early DR was in 1996. Okay, so the first DRs were about 1996 that were commercially available. Imaging receptor plates with thousands of detectors, active matrix arrays, DR, two types, direct and indirect. Okay, so image receptor plates with thousands of detectors have an active matrix array, and there's two different types, direct and indirect. We'll talk more when we get to the DR, okay? CR and DR both use electronic signals and in different ways. Okay, we'll discuss more in the upcoming lessons. Some terminology that we'll use throughout is one is a matrix, which is a grid of columns and rows. Okay, and each square section, I should say, it could be rectangular. Each section in the matrix is called a cell. Okay, and these are pixels. Okay, is what the final output's going to be. So pixel each is assigned a pixel value. The pixel value can be is assigned by the bit depth of the system. So the bit depth is the maximum range of pixel values the computer or other hardware devices can store. Typically for radiology, it's 2 to the 14th is the bit depth of the system, which is 16,000 or so. So it could have 16,000 different values for each cell. There's the dynamic range of the system of pixel values, which is the brightness or gray level made available to build up the final image. So the dynamic range is inside the bit depth. The grayscale is the range of the gray that will actually appear on the displayed image. So the grayscale is within the dynamic range. So bit depth is how many different values each pixel can be inside in the system. How many different values each pixel can be that the system can do. All right. Dynamic range is the range of values that's made available, okay, on the image, and we'll talk more about how that comes up later in the class. And then grayscale is the actual final contrast or amount of grays apparent on the final image. Okay. Imaging and communication. So medical imaging increases in speed and accuracy and performance. In the 1990s, Tim Berners-Lee invented, and it's Sir now, invented the World Wide Web. Telecommunications is the transfer of data from the sender to the receiver. So tele means at a distance, okay? If you ever see that, teleradiology means radiology at a distance, or the rad is reading off-site somewhere else, okay? To send the information, the DICOM is used, and the DICOM is a standard format of imaging in radiology. It's digital imaging and communications in medicine is what it stands for, okay? The information about a DICOM is sent as a header with the image information, then storing it becomes an issue. So PACS in 1982 was utilized, the PACS system, which is Packaging Archiving Communication System. And this is right there, picture archive. So so these are some more terms, okay, that we will be using and exploring later in the class, a little later in these lessons. The DICOM, PACS. Okay. Let's go ahead and we'll get into analog versus digital. This will be useful moving forward, knowing the difference. So analog is a continuous signal. There is no break in the signal, often a signal from a mechanical device. Okay, so analog is often represented with, it could be like a sine wave here, okay, where there is no break from the maximum peak to the lowest valley of the information, okay. Radio wave could be analog. X-rays can also be like an analog format, okay. An X-ray, a wave, there's no break, okay, in it. Then digital is a discrete signal. and we may think, well, what is discrete exactly? Okay, so discrete is where there's only information, or there's a bit of information at a certain point, and then at another point there's another bit of information. Okay, and I'm saying bits because a 1 or a 0, which is the binary that we learned earlier about, a 1 or a 0 could be, each one could be considered a bit. So this is 1, 2, 3, 4. This would be like 5 bits of information. There's a 1, a 0, a 1, a 0, and a 1. Okay. Um, Digital is recording a measurement taken at specific intervals. Okay. So the data is known at that moment, is known at that moment of the recording and at no others. Okay, so the measurement was taken right here at this point. It's going to stay that for the output, or for the signal, until it's taken again. It's taken again, now it's at 0, so it's going to change to 0. Okay, and it's going to stay that same way. It could be doing, it could have other values in here of some sort, but it's not being taken at this time. Okay, now it's going to be taken again. It's going to go back to 1. All right. Most everything in modern times is in a digital format. Okay, computers, um, Bluetooth communication or communications, TVs, camcorders, tablets and phones and all this stuff work in a digital format. Okay. Here's a look at digital versus analog. The same wave in analog and digital is represented here. The question is, which one's better, digital or analog? You would think analog might be better because we're getting a continuous signal. Analog is a continuous signal, whereas digital is like discrete. Okay, it has a discrete step right here, discrete step right here, discrete step right here. Depending on the sampling, okay, we can get the nice curve. All right, and we'll talk about sampling later in later lessons also. The digital though has things like data recovery properties. Okay, so if data packets are lost or information is lost at some point, it can be recovered. All right, analog doesn't have that. It also has error correction properties. So if the data is lost, the two devices with each other, it knows that it's lost. It can say, hey, give me that again, like happens all the time in Wi-Fi and things like that. And it says, okay, yeah, you lost that. Here you go. This is this again. Okay. Or there's an error. The device on the other side can detect that there's an error in the information, and it can say this wasn't received properly, or there's something wrong with this chunk of data. What is it again? Or the device itself can just handle the error and continue on in a proper fashion. All right. Analog devices don't work that way. Okay. Analog devices, whatever's coming in is going to be utilized. Okay. Analog is useful though in certain applications like temperature sensors or control systems, and it may be preferred in like music. All right, some people may prefer an analog sound in music rather than a discrete, okay, or digital music. X-rays are a type of analog signal, like we talked about, that passes information about the patient. Usually we're X-raying the patient. So an X-ray is a type of analog signal, okay, that passes information about the patient to the detector. Right? As we talked about before, X-ray is a wave, okay, so it's a continuous signal, all right, and it's collecting data in the form of being absorbed or being transmitted to the detector about what we're X-raying, okay, which is usually the patient. So here's a breakdown of analog versus digital. Okay, so signal analog is a continuous signal, which we talked about, which represents a physical measurement. Digital signals are discrete time signals generated by a digital modulation. Okay, so modulation just means the difference, like up and up and down. Okay, and the modulation will be done by like a time circuitry, or in a computer, it's like the clock. Okay, you say that the processor runs at 4 gigahertz. Okay, giga is billion, and we learned what hertz was in the Principles of Exposure 1 series. So the a hertz is just 1/2 Okay, so that means that if it's 4 gigahertz, that means that 4 billion times every second it's modulating high and low, high and low, high and low. Okay, the clock, all right, of a computer perhaps, or a processor. Okay, uh, waves denoted by sine wave, typically denoted by square waves, as we saw. Representation uses a continuous range of variables of values to represent information. It uses discrete. Digital uses discrete and discontinuous, so not continuous values to represent the information. An example of analog, the human voice and air is one we didn't mention there. And of course, analog electronic devices would be an example of analog. Digital, computers, CDs, DVDs, um, thousands of other devices, right? Data transmissions. So the data transmission of an analog signal is subjugated to deterioration by noise during transmission and read and write cycles. In digital, it can be noise immune without deterioration during transmission and read-write cycles that we talked about. There's error correction and other things that are available. Flexibility, so the flexibility of analog hardware is not very flexible. Okay, it only inputs the hardware, so it only, whatever signals coming in, it is going to deal with it in the same fashion every time, okay, based on the input. And then in digital, hardware is flexible in implementation. So digital hardware is can be controlled by software, so you can change the software. You can it can handle the data in different ways, just like the finger input on the phone, where, as we discussed before, where you tap a place on the phone, it pulls up an app and stuff, and if you tap that same spot, it's not going to do the same function or operate the same way as it just did. Okay, it's going to be different, right? So uses in analog, it can be used in analog devices only, best suited for audio and video transmissions. Okay, and digital is best suited for computing and digital electronics, which is the realm we are going to work in. So the uses of, or in radiology, digital and analog are used together, with the X-ray being analog, right? We'll also learn about that there's light involved during the image acquisition phase, and that and it becomes digitized, okay? And we'll learn about how that happens in the future videos. Imaging in the future, technology in the future, machine learning may take over radiology. Machine learning is just like AI, and computers are going quantum, as we talked about. So the AI, one of the big things is like for reading the images, like radiologists, that it can analyze the image and it can find and it can diagnose the patient. Okay, so so that could be the future of radiology. We'll talk about some electrical components. Some electrical components that will come up throughout this series are capacitors. which is a device that stores electrical energy in an electric field. Resistors is an electrical component that limits or regulates the flow of electrical current in an electronic circuit. Resistors can also be used to provide a specific voltage for an active device, such as like a transistor, okay, or an output device of some sort, okay. And then an inductor is a passive two-terminal electrical component that stores energy in the magnetic field when electrical current flows through it. These are their physical representations here at the top, what they look like, okay, and then the schematic representation of each. All right. The difference between the capacitor and the inductor, okay, they are utilized differently in circuitry for different reasons, but the capacitor stores the electrical field, if we noticed this, and then the inductor stores the magnetic field. So if we remember from what an X-ray is, okay, there's a electrical and a magnetic field, okay, the electromagnetic spectrum, okay, electromagnetism, they both are intertwined together. And the electricity, okay, is no different. All right, the flowing of electrons in a circuit creates a field around it, okay. It's not the actual electrons moving, it's the field that is created around it, okay. And that field has an electrical and a magnetic component, okay. So an inductor deals with the magnetic side of it, and a capacitor deals with the electric side of it, okay. And that's why there's how these devices work in two different ways, okay, because there's two different components to the electricity, okay, to the field that we would call electricity. All right, we'll go ahead and continue talking about a few more components. Transistor, which we talked about before, is a miniature semiconductor that regulates and controls current or voltage. In addition, it could also work as for amplifying or generating electric signals, and it can act as a switch or a gate for them, okay. And there's different types of transistors that are available, okay, and they can act in and they can behave in different ways or be used for different things, all right. But for our purposes, mostly just a switch or gate, okay, that we need to know, what a transistor is purposes. So a diode is a semiconductor device that essentially acts as a one-way switch for current, okay, would flow in this direction. This is the schematic for it. We already looked at the schematics for transistors earlier. The photodiode is a semiconductor device with a p-n junction that converts photons or light into electric current, okay. So a photodiode is a type of diode, and light can come in to it, okay, and then it sends out an electric current, okay. So it can detect light, sends out electric current. Light emitting diode is a semiconductor diode which glows when voltage is applied. So we are probably much more familiar with these, with this component, an LED. So we have a little bit of voltage is applied, like 3.4 volts or so typically, and light is emitted from the diode, okay. Everything we discussed in this video will be expanded upon and will be explored further in the rest of this series, including the components, analog versus digital, and in the next video we'll talk about CR.